Good afternoon. My name is Arnav and I'll be presenting my research about how photons propagate near a black hole where gravity is so extreme that it bends spacetime itself. We all know light travels in straight lines, but when it passes through massive objects like stars or black holes, it gets bent. This is known as gravitational lensing. It's why black holes appear as a dark shadow surrounded by bright light in images taken by telescopes. So what is this research about? It's about investigating the trajectories of photons under immense gravity and the environment that is that of a black hole. How exactly do we do that? So we make an algorithm that simulates and estimates the angles where photons escape the black hole, collide, or even spin around it forever. And another aim of this project is to create a program that can simulate photons near a black hole of any size, radius, and the photons for which can be launched at any distance from the black hole at any launch angle. Why is this study important? It provides insight into gravitational lensing, accretion disk emissions, black hole images, and shadows. This GIF shows how light, it's not a GIF. The black holes used in the study are all of the Schwarzschild metric, have a radius of 3 kilometers and a mass of 1 solar mass. And they're all non-rotating black holes with no quantum effects. The Schwarzschild metric is the form of a black hole that is spherically symmetrical. To simulate the photon paths, I use a simplified equation derived from general relativity. It's a second-order differential equation, which just means it tells us how the curvature of the path changes as the photon moves. Here, u is related to how far the photon is from the black hole. The term 3u square represents the extreme bending caused in gravity, and the u part is what you'd see in flat spacetime. In this equation, we don't work directly with the distance r, but we use a variable called u. All it means is, as the photon gets closer to the black hole, so as r gets smaller, the value of u gets larger. So u tells us how deep the photon is in the black hole's gravitational pull. It's an inverted way to track distance, which makes the equation easier to work with mathematically. The equation is derived from the geodesic equation for null particles, and we use polar coordinates, and that's how you get the polar coordinates from the Cartesian ones. So once I had the equation, I built a program on MATLAB to simulate the photon's motion. I gave it the mass and radius of the black hole and the launch conditions of the photon, and then calculated its path using a numerical method. Each time I checked if the photon would escape, get pulled in, or orbit. I ran this across many angles and distances, and that's how I made the graphs you'll see next. Something I would like to mention before we talk about the results is, whenever I'm referring to the critical angle, I'm talking about the angle at which the photon collides with the black hole. Here, each photon starts from a distance of 4.5 times 10 to the power 5 kilometers and is launched at a different angle. The blue trajectory follows a circular path without escaping or falling in, and the red trajectory is at a slightly larger angle than the blue one, and it escapes. The green trajectory is at a slightly smaller angle than the blue one, and it's captured by the black hole. This graph demonstrates that just a slight change in the launch angle can drastically change the path. I also want to mention that light is not able to pass through the event horizon. This graph shows how we can increment each angle by just 1 degree and estimate the critical angle where it collides with the black hole, to illustrate the conditions in which the photon will collide with the black hole. In this case, it collides with the black hole at a launch angle of 98 degrees. This graph shows how photon trajectories differ in curved and flat spacetime. The red line shows escape angles in general relativity, which is curved spacetime, while the dotted gray line shows flat spacetime predictions. Notice how they converge near the photon sphere. This indicates a similarity in photon behavior under strong gravitational influence. This graph showcases photon trajectories from within and outside the photon sphere. The blue colored trajectories are all from within the photon sphere, and the green ones are from outside the photon sphere. All of the trajectories are launched at their critical angles. Escape angles increase as you move away from the photon sphere because gravity is relatively weaker outside the photon sphere. This last graph is one where multiple photons have been launched at different launch angles from one point. Most of them fall into the black hole, but something interesting happens at 1.5 Schwarzschild radius. When launched at an angle of pi by 2 or 90 degrees from this point, the photon has a perfectly circular trajectory, one where it never escapes or collides with the black hole but is very unstable, and the slightest deviation can cause it to escape or collide. As you get closer to 90 degrees, the trajectories of photons start to wrap around more before falling in. This is why the photon ring in black hole images appears so sharp. Light bunches up near before crossing the horizon. Okay. These findings verify the existence of a photon sphere, which is the region around a black hole where light is able to orbit in a circular path. Studying these trajectories helps interpret images taken on telescopes like the Event Horizon Telescope, which has taken images of black hole shadows. This study also shows how light propagates in curved spacetime and identifies how small variations in the launch angle can lead to capture or escape. This study is limited by the fact that I used a Schwarzschild black hole, which is spherically symmetrical and non-rotating. I also assumed a perfect vacuum, ignoring plasma, accretion disks and electromagnetic effects that can affect the photon paths. All of these trajectories are also idealized, meaning they cannot be affected by diffraction, dispersion and other phenomena. Future work can involve more realistic black holes by considering black holes that rotate, which is the Kerr metric, quantum effects to incorporate astrophysical environments, black holes with varying masses, and the study can also be expanded into photon rings. Thank you.